In today's video, we are going to learn what a limiting reactant is and how to calculate the limiting reactant and how that impacts the overall reaction. So, the limiting reactant is the reactant that gets used up first. So, it gets used up, and then that would limit the amount of products that are formed. The other reactant or other reactants would be left over, so we would say that there is an excess of them. So, if we take a look at this picture here, we have carbon plus oxygen gas makes carbon dioxide gas. So if you count up what is in here, we have 1, 2, 3, 4, 5, 6, 7, 8. Actually 16 oxygen atoms. As far as carbon goes, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 carbons. In order to make CO2, they react in a 1-to-1 ratio to produce 1 molecule of CO2. So you have to figure out which one would get used up first in the reaction. So there's a couple of different ways you could think about it. When we have something that's a 1-to-1, it's pretty easy because whichever one is less is going to be the one that's consumed first. If the mole ratio is 1-to-2, 2-to-3, that will not always be the case. But if it's 1-to-1, whichever one is less is going to get used up first. So if I have 8 O2 molecules, which would really give me 16 oxygen atoms, that would require 8 carbon atoms to make 8 molecules of CO2, which is what we made. We went 1, 2, 3, 4, 5, 6, 7, 8. So we were able to use up all of the oxygens. We were able to use up 8 of the carbons to produce 8 CO2 molecules. So oxygen was the limiting reactant because it got totally consumed first. It limited the amount of carbon dioxide that we could produce. Carbon was left over in excess because we didn't use all of it. All right, here's another example that should hopefully be very easy to visualize. So let's say I want to make grilled cheese sandwiches. And I, go through my bread and my cheese. And my grilled cheese sandwiches are going to have 1 piece of cheese and then obviously 2 pieces of bread. So let's say I open up the fridge and I have 8 pieces of cheese in my fridge. So I've got 8 pieces of cheese in my fridge. And let's say I go to my pantry and I get my bread out and I have 10 pieces of bread. I want to know how many sandwiches can I make. So if I was going to use up all 8 pieces of cheese, that would require 16 pieces of bread. I do not have that much bread and I don't want to go to the grocery store. So 8 cannot be my limiting reactant. My cheese must be present in excess because I don't have enough bread to react with, or to make a sandwich, not react with. So if I was going to use all 8, I would need 16 pieces of bread. I don't have that. So now let's look at it the other way. If I am going to use up all 10 pieces of bread, if I'm going to use up all 10 pieces of bread, I would need 5 pieces of cheese. So again, that shows me that I would have 3 pieces of cheese left. Therefore, the cheese is going to be my excess reactant. I would use up all 10 pieces of bread, so I would have no bread left, and I would make 5 sandwiches because there's 2 pieces of bread, for each sandwich. So notice how the one with less is not always the limiting reactant because the coefficients do matter. So in this case, my bread would be my limiting reactant. Cheese would be left over in excess. I'd have 3 pieces left, and I would make 5 sandwiches. So now we will start applying this to actual chemical reactions and not just grilled cheese. So why would we purposely add an excess? Well, that means that we can control what is produced, and we can, add a specific amount of, let's say, reactant A, excess of reactant B, and so then we know that the amount of A will impact the amount of our product that is produced. If you are given the amount, either in grams, in moles, even in molarity and volume, if we're dealing with a solution, because then we can figure out the number of moles. So if we're given the amounts of 2 reactants, that is a limiting reactant problem. And we cannot start doing our stoichiometry until we have identified our limiting reactant, because the limiting reactant is going to limit how much of the product can be produced. So here's a example. Part of the SO2 that is introduced into the atmosphere ends up being converted to sulfuric acid. So that's one of the things that contributes to acid rain or acid precipitation. The net reaction is the 2 moles of SO2 react with 1 mole of O2 plus 2 moles of water to produce 2 moles of sulfuric acid. How much sulfuric acid can be formed from 5 moles of SO2, 1 mole of water, 1 mole of oxygen, and an unlimited amount of water? Okay, so we're not going to have to worry about the water because they told us that we had an unlimited amount of that. So now we just have to figure out if the SO2 or the O2 is going to get consumed first. So the way that I look at it is if I use up all 5 moles of SO2. So if I use 5 moles of SO2, that would require 2.5 moles of O2. The reason why, because these are in a 2-to-1 molar ratio. All right, so if I'm going to use all 5 moles of SO2, that would require 2.5 moles of O2. I don't have that much. Therefore, this is not going to work. So that tells me that my SO2 is going to be present in excess. But I always like to double check my work. So then I kind of reverse this. If I'm going to use 1 mole of O2, that would require 2 moles of SO2. Again, because of the mole ratio. And I do have that, so I am good. That makes O2 my limiting reactant. So if O2 is my limiting reactant, that is going to limit how much of the products I can produce, because once that gets used up, the reaction can't happen anymore. So if O2 is my limiting reactant, and if I only have 1 mole of O2, I can produce 2 moles of sulfuric acid because they're in a 1-to-2 ratio. So then O2 is limiting reactant. 1 mole of O2 is present. Therefore, 2 moles of sulfuric acid can be produced. And normally I would write this below, but I was a little short on space, therefore had to shove it in the corner there. Now, one thing that they might also ask is how much of the excess reactant remains. So SO2 is my excess. I started with 5 moles of that, but I only used 2. So I would have 3 moles of SO2 that would remain after the reaction. All right, so we have another example. We have H2 gas, 2 moles of H2 gas, plus 1 mole of O2 gas makes 2 moles of water vapor. And that is the reaction that produces electricity in a hydrogen fuel cell. Suppose the fuel cell contains 150 grams of H2 and 1500 grams of O2. Now, sometimes they will prompt us to find the limiting reactant. Sometimes they might just jump to part 2 or part 3, but since you were given the amounts of both reactants, that should kind of clue you in that you need to find the limiting reactant before you can really solve the problem. So our reaction is already written for us. First thing we want to do is turn these masses into moles because we need the moles in order to compare that to the balanced equation. So we had 150 grams of hydrogen and H2 is going to have a mass of 2.016. And so we've got about 75 moles. But if we want to be exact, we have 74.4 moles of hydrogen that are present. I really like to try to label things as much as possible. Okay, then I'm going to do the same thing with my oxygen. So I've got 1,500 grams of O2 and 1 mole of O2 is equivalent to 32 grams. So I'm just going to do 1,500 divided by 32, and that gives me 46.9 moles of O2 are initially present. Okay, now we need to figure out my limiting reactant. They're not in a 1-to-1 ratio, so we cannot just assume that the one that's less is the limiting reactant. We have to look at it. And again, you can start with either one. It doesn't really matter. So let's say we start by looking at hydrogen. So then I write out if my 74.4 moles of hydrogen reacts completely, I would need, or I would use, now they're in a 2-to-1 ratio. So I do 74.4 divided by 2, or I could do that in my head. It would need 37.2 moles of O2. And I have that. So because I have that, that tells me that O2 is present in excess. And H2, since that can get completely consumed, is my limiting reactant. Now, a lot of times I like to double check my work, so I kind of do it in the opposite direction. If I had used up all 46.9 moles of O2, then I would have needed 93.8, because of the 1-to-2 ratio, moles of hydrogen. And I don't have that many, so that just confirms that I did it correctly. And I just like that because it makes me feel a little bit more confident. Now we're just going to continue on to another slide since we're running out of room. All right, so I copied over my major information, the moles of hydrogen that were present, moles of O2 that are present, and the moles of O2 that I would use, and the fact that hydrogen is the limiting reactant, oxygen is excess. So I have to base my calculations off of the limiting reactant because that is what will limit the amount that's produced, because once it runs out, the reaction would stop. So if I have 74.4 moles of hydrogen present, then I just use stoichiometry, and I could have started back again with the grams, but if I already have the moles, I might as well start with that. So I just use stoichiometry to get from moles of hydrogen to moles of water vapor. And that had a 2 in front of it, and that also had a 2 in front of it. So you could have also done 1-to-1 ratio. And then I'm looking for grams. So 1 mole of water is 18.016 grams. So now I'm just going to do the 74.4 times 18.016, and that gives me an answer of 1340 grams of water that would be produced. Okay, my third question was the grams of excess will remain at the end of the reaction. Okay, so first thing I'm going to do, my excess was O2. I started with 46.9, not grams, 46.9 moles of O2 present, minus the 37.2 that I would use. Now remember, that came from the previous slide when we figured out that O2 was excess, because we would only use the 37.2. That means that 9.7 moles of O2 will remain. So then I just do 9.7 moles of O2 that remain and set that up. I know that 1 mole of O2 is equal to 32 grams. So 9.7 times 32 gives me 310 grams. O2 remain, and that is my answer. Now, if I was looking at a diagram, at a particle diagram of this, at the end of the reaction, I would have produced water. There would be no H2 molecules present because they got used up, but there would be O2 molecules present. So if we were looking at a picture of this, that is what we would expect to see.